In 1994, a Mexican physicist published an equation that broke the unspoken rules of space travel. Miguel Alcubierre showed that Einstein's own theory of general relativity mathematically permits a bubble of warped spacetime that could carry a spacecraft across the cosmos without violating the speed of light. The universe would move around the ship while the ship sat perfectly still. The idea was elegant, thrilling, and immediately impossible. It required more energy than the observable universe contains. For 30 years, the concept collected dust. Then, between 2022 and 2025, a handful of theoretical physicists quietly changed the math. They did not build a warp drive. They did something far more subtle. They showed the impossibility might not be absolute. If you want to understand what these physicists actually achieved, why the results are significant, and why they still do not bring interstellar travel one step closer to reality, hit that like button and subscribe. Now, let's begin. In 1915, Albert Einstein published a set of equations that redefined reality. His general theory of relativity replaced the old Newtonian picture of gravity as a force pulling objects together and introduced something far stranger. Mass and energy do not pull, they curve. They bend the fabric of space-time itself, and everything moving through that curved fabric follows the contours like a marble rolling across a warped rubber sheet. Planets orbit stars not because an invisible rope yanks them inward, but because the star's mass creates a valley in space-time, and the planet traces the curved walls of that valley. This was not a metaphor. It was a mathematical description of physical reality confirmed by observation after observation for more than a century. Light bends around massive objects. Clocks tick slower near gravitational fields. Gravitational waves ripple through space-time when black holes collide. Every prediction Einstein's equations have made has been verified to extraordinary precision by experiments conducted on Earth and observations gathered from the farthest reaches of space. But here is the thing about powerful equations. They do not care about human expectations. Einstein's field equations describe how matter and energy shape the geometry of space-time. You feed in a distribution of energy. The equations hand back a shape, a curvature, a geometry. Most of those geometries are perfectly sensible. They describe stars, planets, black holes, the expanding universe, structures we observe every day through telescopes and gravitational wave detectors. But the equations are indifferent to whether humans find their outputs comfortable. They permit geometries that no one expected, geometries that seem to bend the rules of what the universe should allow. For most of the 20th century, physicists accepted a deep and well-founded conviction about faster-than-light travel. It was impossible, not just difficult, not just beyond current technology. Fundamentally, categorically, and permanently impossible. This conviction was not a guess or a conservative assumption. It was built on decades of experimental confirmation stretching back to Einstein's special theory of relativity published in 1905. Special relativity established a cosmic speed limit. Nothing carrying mass or information can travel through space faster than approximately 186,000 miles per second, the speed of light in a vacuum. The reasoning behind this limit is not arbitrary. It emerges from the mathematical structure of space-time itself. As any massive object accelerates, its kinetic energy increases. In Newtonian mechanics, this increase is proportional and manageable. But special relativity revealed that the relationship between velocity and energy is not linear. As an object approaches the speed of light, its effective mass increases without bound. The energy required to accelerate it further climbs not gradually but explosively, racing toward infinity as the velocity approaches light speed. Reaching exactly the speed of light would demand infinite energy. Exceeding it would require something beyond infinite, a concept that has no meaning in physics or mathematics. The speed limit was not a wall that might someday be broken with a bigger hammer. It was a structural feature of how space and time relate to each other, woven into the geometry of the universe at the deepest level. The consequences of this limit extended far beyond the question of how fast a spacecraft could travel. Special relativity also revealed that the concept of simultaneity, the idea that two distant events can happen at the same time, depends on the observer's state of motion. Different observers moving at different velocities disagree about which events are simultaneous. This disagreement is not a matter of perception or measurement error. It is a fundamental feature of space-time geometry, and it has a devastating implication for anything traveling faster than light. If an object or signal could exceed light speed, certain observers would see that object arriving at its destination before it departed from its origin. The effect would precede the cause. Causality, the principle that causes must come before their effects, would be violated. You could, in principle, construct scenarios where information travels backward in time, creating paradoxes that undermine the logical coherence of physics itself. This was not a minor philosophical objection. Causality is the bedrock upon which all of physics rests. Every equation, every prediction, every experimental confirmation assumes that causes precede effects. If faster-than-light travel were possible within the framework of special relativity, the entire logical structure of modern physics would collapse into paradox. This is why the prohibition against superluminal travel was treated not as a technological limitation but as a law of nature. It was as fundamental as conservation of energy or the impossibility of perpetual motion. For nearly 90 years, from Einstein's 1905 paper to the early 1990s, no serious physicist proposed a mechanism for circumventing this barrier within the accepted framework of physics. Science fiction ignored this constraint entirely. Warp drives, hyperspace jumps, faster-than-light engines became standard furniture in speculative storytelling. Audiences accepted these devices as necessary narrative shortcuts for interstellar plots. Nobody seriously expected real physics to offer anything resembling a loophole. The universe had spoken through its mathematics. The speed of light was the wall, and no amount of clever engineering could punch through it. Then, in 1994, a theoretical physicist named Miguel Alcubierre published a paper that changed the terms of the conversation entirely. Alcubierre was born in Mexico City, studied physics at the National Autonomous University of Mexico, and completed his doctoral work in gravitational physics at Cardiff University in Wales. His specialty was general relativity, specifically the mathematics of how space-time curves in response to different configurations of matter and energy. He was not building spacecraft. He was not working for a space agency. He was not an engineer or an inventor. He was solving equations. And the equations told him something extraordinary. The paper appeared in the journal Classical and Quantum Gravity under a deceptively modest title. It was called The Warp Drive, Hyperfast Travel Within General Relativity. In 11 pages, Alcubierre demonstrated something that should have been impossible given everything physicists believed about the speed of light. He showed that Einstein's own field equations permitted a configuration of space-time geometry in which a region of flat, undistorted space could be enclosed within a bubble. The space ahead of the bubble would contract, compressing itself like an accordion being squeezed shut. The space behind the bubble would expand, stretching outward like a rubber band being pulled apart. The flat region inside the bubble, where a hypothetical spacecraft would sit, would remain perfectly calm. No acceleration, no crushing gravitational forces, no time dilation relative to the interior. The ship would not be moving through space at all. Space itself would be moving around the ship. This distinction is critical and it demands careful explanation because everything that follows in this entire story depends on understanding it precisely. When physicists say nothing can travel faster than light, they mean nothing can move through space faster than light. An object sitting in space and firing its engines cannot accelerate past that cosmic speed limit. The prohibition from special relativity is absolute and applies to every material object and every information-carrying signal moving through the fabric of space-time. But general relativity contains a separate rule that most people never hear about and that changes everything. Space itself has no speed limit. The fabric of space-time can expand or contract at any rate the equations permit without violating any law of physics whatsoever. This is not speculation or theoretical hand-waving. It is confirmed observation verified by decades of cosmological measurement. During the first fraction of a second after the Big Bang, the universe underwent a period called cosmic inflation during which space expanded exponentially faster than the speed of light. Regions that were adjacent before inflation ended up separated by distances that light could not cross in the age of the universe. This did not violate relativity because no object moved through space faster than light. Space itself expanded, carrying everything with it. Galaxies at the edge of our observable universe are currently receding from us at speeds exceeding light speed, not because they are flying through space that fast, but because the space between us and them is expanding at that rate. No law of physics is violated. The galaxies are stationary or nearly stationary relative to their local space. The space itself is doing the moving. Alcubierre's insight was to exploit this asymmetry between local motion and global expansion. If space can expand and contract without limit, then a carefully shaped bubble of space-time curvature could carry an object across cosmic distances at effectively superluminal speeds without the object ever exceeding light speed locally. The ship inside the bubble would be at rest relative to the flat space surrounding it. An observer standing on the ship would feel no acceleration, experience no time dilation beyond normal gravitational effects, and detect no violation of special relativity within their local reference frame. Yet relative to a distant observer watching from outside the bubble and everything inside it could cross distances faster than light, could traverse the same path through undistorted space. The ship cheats the speed limit not by breaking it but by changing the playing field. It does not move through space faster than light. It rides a wave of space-time that carries it while the ship itself sits perfectly still. To grasp how this geometry actually works, imagine a conveyor belt stretching between two cities. A person standing on the belt does not walk. They remain stationary relative to the belt's surface. But the belt itself moves, carrying the person from one city to the other. The person never exerts effort. They never accelerate relative to their immediate surroundings. Yet they arrive at the destination faster than someone walking alongside the belt on solid ground. Now imagine that conveyor belt is not a physical object, but the fabric of space-time itself. The contraction of space ahead of the bubble pulls the destination closer to the bubble, reducing the distance the bubble needs to cross. The expansion of space behind the bubble pushes the origin farther away, effectively adding distance behind the bubble that has already been traversed. The bubble surfs between these two distortions, carried forward by the geometry of the universe rather than propelled by any engine or reaction mass. The ship inside does not accelerate through space. Space accelerates around the ship, and because space has no speed limit, the effective velocity of this transport mechanism can in principle exceed any value, including the speed of light. Now here is where precision becomes absolutely essential, because the distinction between what Alcubierre produced and what the public imagined he produced has been the source of 30 years of confusion and inflated expectations. Alcubierre did not design a machine. He did not propose a propulsion system. He did not sketch engineering diagrams or suggest materials for construction. He did not file a patent or present a blueprint to any space agency. What he produced was a metric. And understanding what a metric is in general relativity is the key to understanding everything about this story. From the initial excitement to the decades of frustration to the recent developments that inspired the title of this video, in general relativity, a metric is a mathematical object that describes the geometry of space-time at every point within a region. It is not a physical device. It is not a set of instructions for building anything. It is a description of a shape. The metric tells you how distances and time intervals relate to each other across curved space. It encodes the complete geometric information about a region of space-time in a set of mathematical functions that can be written down, analysed, and manipulated using the tools of differential geometry. Think of it as an extraordinarily detailed map that describes not just the positions of things in space, but the way space itself bends and stretches and curves around those things. The Schwarzschild metric describes the spacetime geometry around a non-rotating black hole. It tells physicists exactly how space curves, how time slows, and how light bends near such an object. But the Schwarzschild metric did not build a black hole. It described one. The Friedmann-Lemaitre-Robertson-Walker metric describes the geometry of an expanding universe. It tells cosmologists how distances between galaxies change over time and how the curvature of space evolves as the universe ages. But this metric did not create the expanding universe. It described the expansion that was already happening. Each metric is a solution to Einstein's field equations, a specific shape that space-time can take given certain distributions of energy and matter. Finding a new metric means finding a new shape that the equations permit. It does not mean building that shape or even demonstrating that the shape can be built. The Alcubierre metric described a shape, a bubble-like geometry with flat interior space, contracting space ahead and expanding space behind. The equations were valid. The mathematics was consistent with general relativity. The geometry did not violate any fundamental symmetry or mathematical constraint within Einstein's framework. It was a legitimate solution to the field equations of our best-tested theory of gravity. But it was a solution on paper, a mathematical object, a description of a space-time shape that the theory permits, in the same way that the theory permits black holes, gravitational waves, and the expanding universe. Whether that shape could be produced in the physical universe was an entirely separate question that the metric itself could not answer. This distinction between mathematical permission and physical realization is not unique to warp physics. It pervades all of general relativity and represents one of the theory's most fascinating and frustrating characteristics. The theory permits solutions describing traversable wormholes, tunnels connecting distant points in space through shortcuts in space-time geometry that would allow travelers to step from one region of the universe to another without crossing the intervening distance. These solutions are mathematically valid, internally consistent, and fully compatible with the structure of Einstein's equations. But producing them would require conditions that may not exist anywhere in the observable universe, including exotic matter with negative energy density, the same ingredient the warp bubble demands. The theory permits solutions describing closed time-like curves, paths through space-time that loop back on themselves and effectively allow travel into the past. These solutions are mathematically consistent and have been studied extensively by some of the most brilliant minds in theoretical physics, including Kurt Gödel, who found a rotating universe solution containing closed time-like curves as early as 1949. But they require space-time configurations so extreme that most physicists doubt they can be physically produced in any realistic scenario. General relativity is a generous theory. It permits a vast and largely unexplored menu of geometric possibilities, shapes and configurations of space-time that range from the mundane to the exotic to the seemingly impossible. Nature appears to be far more selective than the equations. It produces only a subset of what the mathematics allows, and determining which subset requires examining the physical ingredients each geometry demands, with merciless specificity. A geometry that requires ingredients the universe does not provide is mathematically real but physically empty, a shape on paper that corresponds to nothing in the cosmos. Alcubierre understood this from the beginning. His 1994 paper was explicit about the limitations of his result. The metric described a geometry. Producing that geometry required feeding a specific distribution of energy and matter into Einstein's field equations. When Alcubierre calculated what kind of energy distribution his bubble demanded, the answer was devastating. The warp bubble required negative energy density, not low energy, not zero energy. Energy less than zero, energy below the vacuum of empty space itself. Matter with this property is called exotic matter, and at the time of Alcubierre's paper, no known substance, field, or quantum phenomenon could produce it on the scales required. The reaction within the physics community was immediate and sharply divided along lines that would define the debate for the next 3 decades. On one side, theorists recognized the elegance and mathematical legitimacy of the solution. General relativity is the most thoroughly tested theory of gravity in history. Its predictions have been confirmed across scales ranging from laboratory experiments on Earth to observations of binary pulsars thousands of light years away. If the equations permit a geometry, that permission carries genuine scientific weight. It means the underlying mathematics of reality does not forbid this shape. Dismissing a valid solution to Einstein's field equations would require either finding a mathematical error in the derivation, which no one could identify despite intense and sustained scrutiny from multiple independent research groups, or proving that the required energy conditions are physically impossible under every conceivable circumstance in every possible physical context, which no one had accomplished either. The metric demanded respect because the theory it emerged from had earned that respect through a century of flawless predictive performance across every domain where it had been tested. On the other side, the energy requirements were so extreme, so far beyond anything observed in nature or achievable through any known process, that many physicists viewed the metric as nothing more than a mathematical curiosity, technically correct but physically irrelevant to the actual universe in which we live. Producing negative energy density on the scale required by the bubble seemed not just difficult but categorically beyond any foreseeable capability, separated from reality by a chasm that no bridge could span. Early estimates suggested the bubble would require exotic matter with a total negative energy equivalent to the mass energy of a planet the size of Jupiter. Subsequent analyses by other researchers revised this figure dramatically upward as more careful calculations were performed. Some calculations placed the requirement at the mass energy of a star, others estimated it at the mass energy of an entire galaxy. A few rigorous analyses suggested the warp bubble would demand negative energy exceeding the total mass energy of the observable universe itself. Every star, every galaxy, every particle of matter and radiation in the cosmos converted to energy and multiplied beyond what exists. These were not engineering challenges waiting for better technology. Engineering challenges involve problems that are difficult but solvable with sufficient resources, time, and ingenuity. Building a rocket to reach orbit was an engineering challenge. Constructing a fusion reactor remains an engineering challenge. The energy requirements of the Alcubierre metric were not in that category. They existed in a realm where the gap between requirement and capability was not measured in decades or centuries of technological progress. It was measured in powers of 10 so vast that the word impossible seemed like an understatement. Yet the idea refused to die, and the reason it refused to die reveals something important about how theoretical physics operates at its deepest level. General relativity is not an ordinary scientific theory. It is a framework, a mathematical language for describing how spacetime behaves under all conditions, from the gentle curvature near Earth to the extreme warping inside black holes. Within that language, the menu of possible geometries is enormous and largely unexplored even after a century of research. Some geometries describe things we observe every day. Others describe things we have never observed but cannot rule out: wormholes, closed time-like curves, and warp bubbles. The theory permits all of these shapes without preference or prejudice. The question for each one is whether nature provides the ingredients to produce them. When a valid solution to Einstein's equations is found, it enters the mathematical landscape of general relativity permanently. It cannot be removed by disagreement or discomfort, or by pointing out that it seems impractical. It can only be excluded by proving that the energy conditions it requires are physically impossible under every conceivable circumstance, in every possible context. And proving a universal negative in physics is extraordinarily difficult. The history of science contains numerous confident declarations that something was impossible, followed by discoveries that proved otherwise. Physicists in the 19th century declared that heavier-than-air flight was physically impossible based on their understanding of aerodynamics. Physicists in the early 20th century declared that nuclear energy could never be harnessed for practical purposes. Lord Kelvin is widely quoted as having stated that radio had no future. This does not mean the warp bubble will inevitably become real. History contains far more examples of things that remained permanently impossible than things that surprised everyone by becoming feasible. But it does mean that dismissing a valid mathematical solution to the most successful theory of gravity ever formulated requires extraordinary care and extraordinary proof. The Alcubierre metric persisted in theoretical physics, not because physicists were dreamers or science fiction enthusiasts, but because the mathematics was sound, because the theory it emerged from had earned profound trust, and because no one could definitively prove that its energy requirements were forever and absolutely beyond the reach of any possible physics. The paper also sparked a wave of follow-up research that would continue for 3 decades. Other physicists began exploring the mathematical landscape around the Alcubierre solution, probing its properties, testing its boundaries, and searching for modifications that might soften its brutal energy requirements. Could the geometry be altered to reduce the need for exotic matter? Could the bubble shape be adjusted to minimize the negative energy concentrated in the walls? Could alternative formulations preserve the core idea of effective superluminal travel while avoiding the worst problems of the original metric? One of the earliest significant modifications came from Chris van den Broek in 1999, who showed that altering the bubble geometry could reduce the total exotic matter requirement by many orders of magnitude, though the remaining amount was still far beyond physical reality. José Notario, a Portuguese mathematician specializing in general relativistic geometries, contributed another important development in 2002 by demonstrating that the warp bubble did not require expansion of space behind the ship at all. The original Alcubierre metric used both contraction ahead and expansion behind in a symmetric arrangement, treating the two distortions as equal and opposite components of the same mechanism. Notario showed that an entirely alternative geometric approach, one based on a sliding motion of spacetime, rather than the symmetric push-pull of the original formulation, could achieve a similar transport effect with fundamentally different mathematical properties and a different energy profile. His approach opened new avenues for analyzing the energy requirements from a completely different mathematical direction, and suggested that the space of warp-like solutions was larger and more geometrically diverse than the single solution Alcubierre had discovered. These early modifications established a pattern that would define the next 2 decades of warp research. Theorists would take the Alcubierre metric, alter its mathematical structure in some specific way, adjusting a parameter here, modifying a geometric function there, changing the shape of the bubble wall, or the profile of the energy distribution, and then check whether the modified geometry relaxed the energy conditions compared to the original. Each modification produced a new solution to Einstein's field equations. Each solution came with its own set of energy requirements, stability properties, and physical implications that had to be worked through with careful mathematical analysis. The range of possible warp geometries turned out to be larger than a single solution, containing families of related configurations with continuously variable parameters and different properties. There were families of solutions, continuous ranges of parameters that could be tuned, geometric degrees of freedom that could be explored in multiple directions simultaneously. The bubble was not a single object, but a category containing many members, each with slightly different properties. But none of these early modifications solved the fundamental problem that haunted every version of the concept. Every single variation, without exception, still required negative energy density. The total quantity decreased over the years as geometric optimizations accumulated, falling from the mass energy of the observable universe down through galactic scales to stellar scales. The trajectory was downward, which some found encouraging, but the qualitative barrier remained firmly and immovably in place at the bottom of every calculation. You needed exotic matter, and exotic matter in the quantities required did not exist anywhere in the observed universe and could not be produced by any known physical mechanism. The concept drifted into a strange twilight within theoretical physics, too mathematically rigorous to dismiss as pseudoscience or science fiction speculation, too physically unrealizable to pursue as a practical pathway to the stars or even as a serious research program aimed at engineering outcomes. Papers continued to appear in respected journals, each one exploring some new mathematical corner of the warp geometry landscape, each one contributing another piece to the growing map of what Einstein's equations permitted. But the wider community had largely moved on to problems where the gap between theory and physical reality seemed bridgeable within some conceivable time frame. And yet the equations remained, sitting undisturbed in the mathematical framework of general relativity, unaffected by the practical objections, undiminished by the energy calculations. Indifferent to the consensus of the physics community, the Alcubierre metric was still a valid solution to Einstein's field equations. The geometry was still permitted by the theory. The shape was still there, embedded in the mathematics, waiting inside the theory like a locked room in an enormous mansion, a room whose key had been declared non-existent by every locksmith who had ever examined the door, but whose existence could not be denied, because the blueprints of the mansion clearly showed it was there. And haunting the entire enterprise was a question that would take 30 years and an entirely new generation of mathematical approaches to even begin answering. Was the impossibility truly absolute, rooted in the deepest structure of physical law with no exceptions under any circumstances? Or did the mathematical landscape contain corners that no one had yet thought to explore, regions where the rules might bend in directions that 3 decades of research had failed to anticipate? The answer would require understanding not just what was wrong with the warp bubble, but precisely how wrong it was, in how many independent ways the impossibility manifested, and whether any of those manifestations contained hidden flexibility that could be exploited by a sufficiently clever reformulation of the underlying mathematics. What came next was not a solution. It was a deeper understanding of just how formidable the obstacles truly were. To understand why the Alcubierre metric terrified physicists, you need to understand what negative energy density actually means, not the vague, hand-waving version that appears in popular science articles. The precise mathematical version that made some of the brightest minds in theoretical physics close the book on warp research and walk away. Start with ordinary matter. Everything you have ever touched, seen or measured has positive energy density. A rock sitting on a table has positive energy. The photons streaming from a light bulb have positive energy. The neutrinos passing through your body right now, billions of them every second, have positive energy. The coffee in your mug, the air in your lungs, the iron core of the earth beneath your feet. Positive energy. Always positive. Even the vacuum of empty space, stripped of every particle and every field excitation, has a baseline energy that quantum field theory defines as 0 or slightly above 0 depending on how you handle the mathematical accounting. Positive energy density is the default state of everything in the observable universe. It is so universal, so absolute, so thoroughly confirmed by every measurement ever taken across every branch of physics, from particle accelerators to cosmological surveys, that most physicists never need to think about the alternative. It is like asking a fish to contemplate the absence of water. The concept does not arise, because the reality is everywhere and always present. Negative energy density means something profoundly different. It means a region of space-time where the energy content drops below the vacuum baseline, below 0, below empty. It is not merely the absence of energy, the way darkness is the absence of light. It is not a battery that has been drained to nothing. It is energy with a value less than nothing, a deficit deeper than emptiness. If the vacuum of empty space represents the ground floor of a building, negative energy density is not the ground floor with the lights off. It is the basement, a level below the foundation that should not exist according to everything we observe about ordinary matter. Matter or fields with this property would curve space-time in the opposite direction from normal matter. Where a star creates a valley in space-time that draws objects inward through gravitational attraction, a concentration of negative energy would create a hill that pushes objects outward, generating what amounts to gravitational repulsion. This reversal is precisely what the Alcubierre bubble needs. The contraction of space ahead of the bubble and the expansion of space behind it require opposite curvatures in adjacent regions, spacetime bending inward on one side and outward on the other simultaneously. Producing those opposite curvatures demands energy configurations, where some regions contain positive energy and others contain energy below the vacuum state. The bubble wall, that thin shell of warped spacetime separating the calm interior from the distorted exterior, must be threaded with rivers of negative energy density flowing in precise geometric patterns dictated by the field equations. Without this exotic ingredient, the geometry collapses. The bubble cannot form. The mathematics returns an unambiguous verdict. You need something that nature does not appear to provide anywhere in the observable universe at any scale. This is not merely unusual. In the context of classical general relativity, it is almost unheard of. The theory was built on observations of matter that universally behaves in one direction. Gravity attracts. Mass energy is positive. Spacetime curves in ways consistent with those observations. When physicists formalized this behavior over the course of the 20th century, they codified it into a set of assumptions called energy conditions. These conditions are not laws of physics in the way that conservation of energy or the speed of light are laws. They are not inscribed into the fundamental equations. They are more like guardrails, reasonable assumptions about how well-behaved matter should act, based on everything humanity has ever observed in laboratories, in telescopes, and in particle accelerators. The most important of these conditions for the warp bubble discussion are the weak energy condition, the null energy condition, the dominant energy condition, and the strong energy condition. Each one places a different restriction on how energy and momentum can be distributed through spacetime. Together, they constrain the kinds of geometries that physically reasonable matter can produce. They tell physicists which solutions to Einstein's equations correspond to things that could actually exist in the real universe, and which solutions are mathematical ghosts, shapes permitted by the equations but forbidden by the matter available to fill them. The weak energy condition states that any observer moving through spacetime should measure a non-negative energy density. No matter how fast you travel, no matter what direction you look, no matter what reference frame you occupy, the energy you measure should be zero or positive, never negative. This is the most basic and intuitive of the conditions. It simply says that energy density cannot drop below zero for any physical observer anywhere in the universe. The null energy condition is closely related but applies specifically to observers traveling at the speed of light, which in practice means it constrains how photons and other massless particles experience the energy distribution of spacetime. The dominant energy condition adds a further restriction, requiring that the flow of energy through spacetime cannot exceed the speed of light. Energy must move in physically reasonable ways, not teleporting or propagating faster than causality allows. The strong energy condition states that gravity is always attractive on net when you account for the full energy momentum content of matter. It prevents configurations where ordinary matter generates repulsive gravity, pushing objects apart rather than drawing them together. The Alcubierre metric violates all of them. Not subtly, not at the margins, not in some obscure corner of parameter space where the violations are so small they might be dismissed as mathematical artifacts or swept under the rug of rounding errors. The warp bubble geometry requires energy distributions that shatter every single one of these conditions in the regions surrounding the bubble wall. The violations are most severe along the bubble boundary itself, the thin shell of warped spacetime separating the flat interior from the distorted exterior. Along this shell, the energy density must plunge deep into negative territory. Not slightly below zero, profoundly below zero. The mathematical expressions describing the energy content of the bubble wall contain terms that are unambiguously, unavoidably, and enormously negative. There is no way to rearrange the geometry, no clever choice of coordinates, no mathematical trick, no alternative interpretation of the variables that makes the negative energy disappear. It is baked into the structure of the solution as fundamentally as the curvature itself. This is why the physics community reacted with such profound skepticism despite the mathematical validity of the metric. General relativity permits the geometry. But nearly every major theorem about the behavior of spacetime relies on at least one of these energy conditions being satisfied. The singularity theorems of Roger Penrose and Stephen Hawking, which prove that black holes must contain singularities, assume the null energy condition holds. The topological censorship theorems, which prevent naked singularities from being visible to distant observers, require energy conditions. The positive mass theorem, which guarantees that isolated gravitational systems have non-negative total energy, depends on them. Violating these conditions does not just open the door to warp bubbles. It opens the door to time machines, naked singularities, traversable wormholes, and a host of other exotic geometries that most physicists consider unphysical. If you accept that energy conditions can be violated freely and at macroscopic scales, the mathematical floodgates open, and general relativity permits structures that would tear the logical fabric of causality itself. This is why the energy problem was never treated as merely a matter of insufficient technology. It was not like the challenge of building a more powerful rocket or developing a better fuel. It was treated as a fundamental barrier rooted in the deepest principles of how space-time and matter interact. Building a bigger power plant does not help when the problem is that the type of energy you need contradicts the observed behavior of every form of matter in the known universe. Now, the obvious question: has negative energy density ever been observed anywhere in nature? The answer is yes, but with caveats so severe they essentially reinforce the impossibility rather than undermining it. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997 by Steve Lamoureux at the University of Washington, provides the only confirmed laboratory demonstration of a phenomenon involving negative energy density relative to the vacuum state. The setup is remarkably simple in principle. Place two uncharged metallic plates extremely close together in a vacuum, separated by a gap of roughly a few hundred nanometers, a distance smaller than a single wavelength of visible light. Quantum field theory predicts that the vacuum between the plates differs from the vacuum outside them. The plates restrict which quantum fluctuations can exist in the gap. Only fluctuations with wavelengths that fit neatly between the plates are permitted. Longer wavelengths are excluded because they simply cannot squeeze into the space. Outside the plates, all wavelengths are allowed without restriction. This asymmetry creates a measurable imbalance in radiation pressure. More quantum fluctuations push on the plates from outside than from between them. The result is a measurable attractive force pushing the plates together. The energy density between the plates drops slightly below the normal vacuum energy outside, producing what can be characterized as a region of negative energy density relative to the external vacuum baseline. The effect is real. It has been measured repeatedly with increasing precision over the past 3 decades by multiple independent research groups using different experimental techniques. It represents a genuine quantum phenomenon where the energy density in a confined region falls below the surrounding vacuum baseline, and it falls astronomically, incomprehensibly, laughably short of what a warp bubble would require. The magnitude of the Casimir effect is extraordinarily tiny. The force between the plates is measured in micronewtons or less, detectable only with sensitive laboratory instruments under carefully controlled conditions. The negative energy density it produces exists only across gaps smaller than a micrometer. The total amount of negative energy involved is vanishingly small, orders of magnitude below what would be needed to affect space-time geometry in any detectable way. Scaling this effect up to the dimensions required for a warp bubble, even a microscopically small one, would require increasing the energy density by factors that dwarf the ratio between an atom and the observable universe. The Casimir effect demonstrates that quantum physics can produce small, localized, transient deviations below the vacuum energy state. It does not demonstrate that macroscopic, intense, sustained regions of negative energy density are physically achievable. Comparing the Casimir effect to the energy requirements of the Alcubierre metric is like comparing the static electricity in a wool sweater to the total energy output of a supernova. They are the same type of phenomenon in the loosest possible theoretical sense, and the gap between their magnitudes spans more orders of magnitude than the human mind can meaningfully process. If the Casimir effect is a single drop of water, the warp bubble needs an ocean larger than the Pacific multiplied by itself 100 times over. The two quantities exist in the same mathematical category, but in completely different physical universes of scale. Making matters considerably worse, theoretical work in the 1990s and early 2000s established a set of results called quantum inequalities that place strict fundamental limits on how much negative energy can exist in a given region and for how long it can persist. These inequalities, developed primarily by Larry Ford at Tufts University and Thomas Roman at Central Connecticut State University, through rigorous mathematical derivations within the framework of quantum field theory, showed that nature imposes a non-negotiable trade-off between the magnitude, duration, and spatial extent of any negative energy fluctuation. The relationship is inverse and absolute. The more negative the energy density in a region becomes, the shorter the duration it can persist, and the smaller the volume it can occupy. Large amounts of negative energy must be compensated by even larger amounts of positive energy in the immediate vicinity, and the compensation must happen quickly. The negative energy pulse must be extremely brief, appearing and vanishing on timescales too short to sustain any macroscopic geometric effect on spacetime curvature. You cannot simply accumulate negative energy in a container and store it for later use the way you might charge a battery or fill a fuel tank. The universe enforces a strict budget with no possibility of deficit spending, and every withdrawal from the negative energy account must be repaid with compounding interest in positive energy nearby. The deeper you go into negative energy territory, the faster and more completely you must repay the debt. Ford and Roman applied these quantum inequalities directly to the Alcubierre metric and reached devastating conclusions. The constraints implied that any physically realizable version of the warp bubble would face energy requirements even more extreme than the original classical estimates suggested. The quantum inequalities did not merely confirm the difficulty of producing the required exotic matter. They added an entirely new layer of impossibility by showing that even if you could somehow generate negative energy in the required quantities through some unknown mechanism, the laws of quantum field theory would prevent you from maintaining it in the configuration the bubble demanded. The negative energy could not be sustained long enough or concentrated densely enough or distributed precisely enough to maintain the warp geometry for any operationally meaningful duration. The bubble would collapse before it could form. This result struck at the heart of any hope that future technology might overcome the energy barrier. The quantum inequalities are not technological limitations. They are not constraints imposed by the crudeness of our instruments or the immaturity of our engineering. They are consequences arising from the mathematical structure of quantum field theory itself, our best-tested theory of how matter and radiation behave at fundamental scales. Overcoming them would require not just new engineering, but new physics, a complete revision of quantum field theory that somehow loosened the restrictions it places on negative energy. And quantum field theory has been confirmed by experiments to a precision of better than 1 part in 10 billion, making it arguably the most accurately tested scientific theory in human history. Proposing to modify it specifically to rescue a warp drive would be an extraordinary claim requiring extraordinary evidence, and no such evidence existed. But the raw energy calculations themselves deserve closer examination because their sheer absurdity played a crucial role in shaping how the physics community viewed the warp concept for the next 2 decades. The numbers did not merely discourage researchers, they made the entire enterprise appear fundamentally disconnected from physical reality. When Alcubierre published his original 1994 paper, the energy content of the bubble was not his primary focus. He was presenting a geometric solution to Einstein's field equations and noting its general properties. Subsequent researchers took up the task of calculating exactly how much exotic matter the bubble would require. The answers varied depending on the specific assumptions made about bubble size, wall thickness, velocity, and geometric configuration. But every single calculation, without exception, produced numbers that defied comprehension One of the most cited early analyses was conducted by Michael Fenning and Larry Ford in 1997. They examined a warp bubble large enough to enclose a small spacecraft, perhaps a volume comparable to a modest room capable of holding a few people and some equipment, traveling at approximately 10 times the speed of light. Their calculations showed that the total negative energy required would be approximately 10 times the mass energy of the entire observable universe. Stop and absorb that number. Let it settle into your understanding of what this field was dealing with. 10 times everything. Every star in every galaxy across the entire observable cosmos, every particle of dark matter in every galactic halo, every photon in the cosmic microwave background that has been traveling since the universe was 380,000 years old, every neutrino streaming through the void between galaxy clusters, all of it converted completely into energy using Einstein's mass energy equivalents and then multiplied by 10. And that resulting quantity of energy would need to be negative, a form of energy that no macroscopic object has ever exhibited anywhere in the observed universe. The number was not just impractical, it was not just beyond foreseeable technology, it was a reductio ad absurdum, a result so extreme that it functioned as a proof of impossibility for all practical purposes. Physics had produced a valid geometric solution to its own equations that demanded more energy than the cosmos itself contained. Fenning and Ford also demonstrated a second devastating constraint. The negative energy had to be confined to an extraordinarily thin shell around the bubble. The thickness of this shell scaled inversely with the bubble's effective velocity. The faster the bubble moved, the thinner the shell needed to be. At 10 times the speed of light, the shell would need to be on the order of 10 to the negative 32 meters thick. That number is approaching the Planck scale of 10 to the negative 35 meters, the smallest meaningful distance in physics. The Planck length marks the scale where quantum gravitational effects dominate, and the smooth space-time of general relativity breaks down into something unknown, possibly a foam of quantum fluctuations, possibly something stranger. At that scale, general relativity itself cannot be trusted. The very theory being used to derive the warp geometry ceases to be valid at precisely the scale where the geometry requires its most extreme energy concentrations. This was not a minor technical difficulty that might be resolved with more sophisticated mathematics. It was a signal that the warp bubble was pushing general relativity beyond the boundaries of its own domain of applicability. Physicists do not possess a complete theory of quantum gravity. General relativity describes space-time beautifully at large scales. Quantum field theory describes matter and forces brilliantly at small scales. But the two theories are fundamentally incompatible at the Planck scale, where both gravitational and quantum effects are simultaneously strong. No one knows what physics looks like at that boundary. The warp bubble's energy distribution demanded conditions at exactly this uncharted frontier, where no existing theory can make reliable predictions. Other researchers explored whether modifying the bubble's parameters could bring the energy requirements into more reasonable territory. Chris van den Broek's 1999 modification, which made the bubble's exterior microscopically small while maintaining a macroscopic interior volume through a clever warping of the spatial geometry that exploited general relativity's ability to decouple internal and external dimensions, reduced the total negative energy dramatically. Instead of needing the mass energy of 10 observable universes, his modified geometry brought the requirement down to roughly a few solar masses of negative energy. A few solar masses might sound manageable by comparison to 10 universes, and that comparison itself reveals how thoroughly warped the discussion had become, how completely the numbers had stretched beyond all reasonable physical intuition into a realm where the human capacity for understanding scale simply breaks down. The Sun contains approximately 2 times 10 to the 30th kilograms of mass. Converting that entirely into energy using Einstein's famous equation yields a number so vast that every nuclear weapon ever detonated in human history, every bomb test, every wartime explosion, every megaton of thermonuclear fury humanity has ever produced, represents a rounding error lost in the noise of significant digits, and that entire solar mass equivalent of energy would need to be negative, concentrated in a shell of Planck-scale thickness around the bubble, distributed with perfect mathematical symmetry to maintain the geometry, and sustained indefinitely without fluctuation or degradation for the entire duration of travel across whatever distance the bubble traversed. Each of these sub-requirements represented its own independent impossibility, stacked on top of all the others. By the early 2000s, the catalogue of obstacles had grown into something that looked less like an engineering challenge and more like a wall of fundamental physical law stretching in every direction without gaps. The bubble required exotic matter with negative energy density, a substance never observed at macroscopic scales. The quantity of exotic matter exceeded the mass energy of the observable universe under standard assumptions and remained at stellar mass scales even under the most aggressively optimistic geometric modifications. Quantum inequalities prevented the accumulation, concentration, and sustained maintenance of negative energy in the required configurations regardless of what technology might someday produce it. The energy distribution demanded structures at the Planck scale, where general relativity itself could no longer be trusted as a reliable description of spacetime geometry. No known physical mechanism, no observed quantum field, no detected particle, no theoretical extension of the standard model of particle physics could produce negative energy density in macroscopic quantities. And the only confirmed phenomenon demonstrating any form of negative energy, the Casimir effect, produced densities trillions upon trillions of times too small to be relevant to the warp discussion. The gap was not a factor of 10 or 100 that might yield to technological progress. It was a factor of 10 raised to powers so large that writing them out would consume a paragraph. Any single one of these problems would have been sufficient to discourage a generation of researchers. Together they created an overwhelming case that the Alcubierre metric, while mathematically valid, described a spacetime configuration that nature could never produce. The consensus that formed among the majority of physicists working in general relativity was not that the metric was wrong, it was correct. The consensus was that the metric was irrelevant to the physical universe, a beautiful geometric solution to Einstein's field equations that the actual cosmos had no interest in actualizing. This consensus was reinforced by a broader context within theoretical physics that deserves careful attention because it explains why the resistance to the warp concept was not mere stubbornness or a failure of scientific courage. The energy conditions are not arbitrary assumptions bolted onto general relativity for convenience. They are deeply connected to fundamental principles of quantum field theory, thermodynamics, and the logical structure of causality itself. These connections run through the deepest layers of modern physics. Violating the weak energy condition in a sustained macroscopic way would have implications extending far beyond the narrow question of whether warp drives are possible. It would undermine the second law of thermodynamics, the principle that entropy always increases in closed systems, the principle that gives time its direction and prevents broken eggs from reassembling themselves spontaneously. It would enable the construction of perpetual motion machines of the second kind, devices that extract useful work from systems already in thermal equilibrium, violating everything we understand about heat, energy, and the fundamental arrow of time. Most troublingly and most devastatingly for the logical structure of physics itself, it would permit violations of causality, allowing signals and possibly matter to travel backward in time, creating grandfather paradoxes and closed causal loops that would undermine the very concept of cause and effect. The energy conditions serve as the last line of defense, the foundational constraints protecting physics from a cascade of paradoxes and impossibilities that would make the universe logically incoherent. Allowing their violation for the sake of a warp bubble meant accepting consequences that most physicists found deeply unacceptable on grounds far more fundamental than technological feasibility. This is an important point that rarely appears in popular science discussions of the warp drive. The resistance to the Alcubierre metric among working physicists was not a failure of imagination or an inability to think boldly about the future of space travel. It was not conservatism or intellectual cowardice. It was a reasoned, principled assessment that the physical requirements of the warp bubble conflicted with the foundational architecture of multiple areas of physics simultaneously. Accepting the physical realizability of the warp bubble meant accepting that energy conditions could be violated on macroscopic scales in sustained and controllable ways. And accepting that meant opening doors to time travel paradoxes, thermodynamic violations, and closed causal loops that the entire structure of modern physics was constructed specifically to prevent. The pattern across 2 decades of research was consistent, unambiguous, and unbroken by any exception. You could reshape the bubble, you could optimize the geometry, you could adjust the wall thickness, modify the velocity profile, introduce asymmetries, layer multiple shells, explore every mathematical degree of freedom the equations offered. You could squeeze the energy numbers down by factors of 10, 100, 1,000, 1,000,000. But at the bottom of every calculation, beneath every optimization and every clever modification, sat the same immovable requirement: negative energy density, exotic matter, the substance that does not exist in any observed corner of the physical universe. And yet, as devastating as the energy problem was, it was about to be joined by additional obstacles that would make the already impossible situation appear even grimmer. The warp bubble did not merely require impossible fuel. It had deep structural problems suggesting that even a hypothetical bubble, constructed with unlimited supplies of exotic matter, handed to physicists by some generous deity with no questions asked about where it came from or how it was produced, would still be fatally flawed in ways having nothing to do with energy. Researchers were beginning to discover that the bubble walls would accumulate lethal radiation through quantum effects, analogous to Hawking radiation at black hole horizons, that the pilot inside would be causally disconnected from the bubble boundary and permanently unable to steer, stop, or modify the bubble's trajectory. That quantum field fluctuations at the bubble surface would trigger catastrophic instabilities, destroying the geometry and timescales shorter than any meaningful physical process. The idea was not just energetically out of reach. It was beginning to appear fundamentally broken from multiple independent directions simultaneously, each failure mode reinforcing the others, each new analysis adding another lock to a door that already seemed permanently sealed. And understanding those additional failures requires stepping beyond the energy question entirely into the strange and unforgiving physics of what would happen at the boundary walls of the bubble itself. The energy problem alone should have been enough to bury the warp bubble permanently. But physics has a way of making bad situations worse. Over the 2 decades following Alcubierre's original publication, researchers who continued probing the mathematics of the warp metric uncovered a series of additional problems that had nothing to do with exotic matter or negative energy density. These were structural failures built into the geometry itself. Flaws so fundamental that even if some miraculous breakthrough handed physicists unlimited quantities of exotic matter with precisely the right properties, the warp bubble would still not work. The concept was not merely starved of fuel. It was broken at the architectural level in ways that compounded upon each other, until the idea seemed not just impractical but physically incoherent from multiple independent directions. The first of these additional problems involved radiation, not the kind you shield against with lead panels or magnetic fields. A far more exotic and far more lethal variety arising from the interaction between quantum fields and the extreme spacetime curvature at the bubble wall. In 1974, Stephen Hawking published one of the most important results in 20th century theoretical physics. He showed that black holes are not perfectly black. The extreme curvature of spacetime near a black hole's event horizon interacts with quantum fields in a way that produces a faint thermal glow of particles radiating outward. This Hawking radiation arises because the event horizon separates regions of spacetime so dramatically that the quantum vacuum on one side of the boundary differs from the quantum vacuum on the other. Virtual particle pairs that form near the horizon can be torn apart by tidal forces, with one particle falling into the black hole and the other escaping as real radiation. The effect is tiny for stellar mass black holes, producing temperatures far below the cosmic microwave background, but the principle is profound. Whenever spacetime curvature creates a sufficiently sharp boundary between causally distinct regions, quantum fields respond by producing particles. The wall of an Alcubierre warp bubble creates exactly this kind of boundary. The transition from the flat interior space to the highly contracted or expanded exterior space occurs across a thin shell of extreme curvature. The curvature gradients at this shell are not gentle slopes, they are cliffs. The geometry changes so abruptly across such a small distance that the quantum vacuum on the interior side of the wall exists in a fundamentally different state than the quantum vacuum on the exterior side. Researchers analyzing the quantum field behavior near this shell discovered that the bubble wall would act as a relentless particle factory. Quantum fields interacting with the sharply curved spacetime at the bubble boundary would generate a continuous, unceasing flux of high-energy particles through a mechanism directly analogous to Hawking radiation at a black hole horizon. The effect would be most intense at the front of the bubble, where space contracts most violently, creating conditions where the curvature gradients reach their absolute maximum values and the quantum vacuum is torn apart most aggressively. This was not a minor theoretical footnote. Analysis by researchers including Carlos Barceló, Stefano Finazzi, and Stefano Liberati in the late 2000s showed that the particle production at the bubble wall would be catastrophic. As the bubble accelerated towards superluminal effective velocity, the energies of the produced particles would blue shift dramatically. The front wall of the bubble would accumulate an ever-growing shell of extremely high-energy radiation. This radiation would not dissipate or spread out. It would pile up along the bubble boundary like snow accumulating on the front of a moving plough, except this snow consisted of particles with energies approaching and potentially exceeding those found in the most violent astrophysical events in the universe. The implications were devastating in two distinct ways. First, the accumulated radiation would render the interior of the bubble uninhabitable. Any spacecraft, any equipment, any living organism inside the warp bubble would be exposed to a lethal and continuous bombardment of high-energy particles penetrating inward from the bubble walls. Shielding against this radiation would be utterly meaningless, because the particles were not arriving from an external source that could be blocked by placing material between the source and the occupants. They were being generated by the geometry of space-time itself, created at the very boundary that defined the bubble's structure. The walls of your ship are producing the radiation. You cannot shield yourself from a threat that originates in the fabric of space surrounding you on every side. There is no direction to hide from because the source is omnidirectional, embedded in the architecture of the space-time geometry you are traveling inside. Second, and more fundamentally damaging to the concept, the accumulated energy in the radiation shell would grow without bound as the bubble maintained superluminal effective velocity. This energy buildup would eventually destabilize the bubble geometry itself. The exotic matter configuration sustaining the warp field would need to account for and counterbalance this growing radiation energy. The original calculations of how much exotic matter the bubble required did not include this additional energy burden. When the radiation accumulation was factored in, the already impossible energy requirements became even more extreme. The bubble was not just expensive to create, it was expensive to maintain, with the maintenance cost escalating continuously and without limit for as long as the bubble operated. The radiation problem also introduced a new failure mode upon deceleration. When the bubble slowed down or collapsed, the accumulated radiation shell would be released in a concentrated burst directed forward along the bubble's trajectory. Finazzi and Liberati showed that this burst would carry extraordinary energy, potentially enough to devastate anything in the bubble's path at the destination. The warp bubble would function as a weapon of cosmic proportions, arriving at its target surrounded by a shell of destruction that had been building throughout the entire journey. The faster the bubble travelled and the longer it maintained superluminal speed, the more destructive this arrival burst would be. Reaching a destination safely was not merely a question of generating the exotic matter to create the bubble. It required solving the radiation accumulation problem. a challenge that existed independently of and in addition to every obstacle already identified. The second structural failure was arguably even more disturbing because it attacked the very concept of controlling the warp bubble once created. This is known as the horizon problem, and it arises from the same relativistic principles that make the bubble theoretically interesting in the first place. Recall that nothing within spacetime can transmit information faster than the speed of light. This is not merely a technological limitation, it is a structural feature of causality itself. Effects cannot precede their causes. Signals cannot arrive before they are sent. This principle holds everywhere within the spacetime described by general relativity, including inside and around a warp bubble. The flat space inside the bubble obeys special relativity normally. Light signals travel at light speed relative to the interior space just as they would anywhere else. Now consider what happens when the bubble reaches superluminal effective velocity. The bubble wall moves faster than light relative to the external spacetime. A pilot inside the bubble who wants to send a signal to the front wall, perhaps to initiate deceleration, to change direction, to collapse the bubble upon arrival at the destination, or to make any adjustment whatsoever to the bubble's behavior, faces an impossible task. The signal travels at light speed through the flat interior space, because that is the fastest any signal can travel through any region of spacetime regardless of circumstances. But the front wall of the bubble is effectively receding faster than light speed relative to the exterior reference frame. The geometry of the spacetime surrounding the bubble creates a causal horizon between the interior and certain critical portions of the bubble wall, a one-way boundary through which information cannot pass. Signals from the pilot simply cannot reach the front of the bubble. They are chasing a boundary that is causally disconnected from them, separated by the same fundamental type of horizon that isolates the interior of a black hole from the external universe. Just as no signal can escape outward through a black hole's event horizon, no signal from the bubble's interior can reach the leading edge of the bubble wall once the effective velocity exceeds light speed. This means the pilot has no control over the bubble once it reaches superluminal speed. They cannot steer it, they cannot slow it down, they cannot adjust its trajectory. They cannot signal the bubble wall to change configuration in any way. The ship inside the warp bubble is not piloting a vessel through space. It is trapped inside a self-contained pocket of spacetime that moves according to its own geometry with complete indifference to anything the occupants want or need. The pilot is a passenger, imprisoned in a bubble that was configured before it launched, and that cannot be modified from inside once underway. This control problem has no obvious resolution within the framework of general relativity. Some researchers proposed pre-programming the bubble geometry so that it automatically decelerates at a specified distance. But this would require setting up the exotic matter distribution along the entire planned trajectory before the bubble launches. The warp drive would not be a vehicle you operate. It would be a track you build in advance, laying down exotic matter along the entire route like rails for a cosmic train. This converts the warp bubble from a flexible mode of transportation into an extraordinarily expensive fixed infrastructure project, requiring exotic matter to be distributed across light years of space before a single journey could begin. The concept loses essentially all practical utility, even in the most generous hypothetical scenario. Others proposed that the bubble could be controlled from the outside by an external operator who arranges the exotic matter distribution in real time as the bubble passes through pre-staged regions of spacetime. But this too requires faster-than-light coordination, which is exactly the capability the warp bubble was supposed to provide. The solution requires the problem to already be solved. The logic becomes circular. The horizon problem struck at the conceptual heart of the warp drive as a transportation technology, a vehicle you cannot steer, cannot stop, and cannot modify once underway, is not truly a vehicle in any meaningful sense. It is a projectile, and a projectile that arrives at its destination wrapped in a shell of lethal radiation accumulated during transit is not transportation. It is a weapon. The third structural problem emerged from semi-classical gravity analysis and attacked the stability of the bubble geometry itself. Semi-classical gravity treats spacetime classically, using Einstein's equations as written, but accounts for quantum effects in the matter fields that source the spacetime curvature. It is an approximation, not a complete theory of quantum gravity, but it represents the best available framework for analyzing situations where quantum fields interact with strong gravitational curvature. When researchers applied semi-classical methods to the Alcubierre metric, they found that the bubble wall was inherently unstable in a way that could not be engineered around. Small perturbations in the quantum fields near the wall would grow exponentially rather than dying away harmlessly. Any tiny deviation from the perfectly symmetric exotic matter distribution, any microscopic fluctuation in the energy density at the bubble boundary, any infinitesimal irregularity in the curvature profile of the wall would amplify itself through a positive feedback mechanism, feeding on the extreme curvature gradients at the bubble boundary. The bubble wall would not maintain its mathematically precise shape. It would develop ripples, then distortions, then catastrophic irregularities that would shatter the warp geometry entirely and release the accumulated energy in the bubble wall in an uncontrolled burst. This instability is not the kind of engineering problem that could be solved with better materials, more precise construction techniques, or improved manufacturing tolerances. It is a consequence of how quantum fields fundamentally behave in strongly curved spacetime, rooted in the mathematical structure of quantum field theory itself. The fields are inherently subject to quantum fluctuations, tiny random variations in energy density that cannot be eliminated even in principle because they are mandated by the Heisenberg uncertainty principle. In flat spacetime or gently curved spacetime, these fluctuations are harmless background noise. They average out over time and space, producing no macroscopic effects that matter for large-scale geometry. But in the extreme curvature environment of the bubble wall, these fluctuations interact with the geometry in a way that amplifies them rather than dampening them. The bubble wall acts as a runaway amplifier for quantum noise, converting microscopic fluctuations into macroscopic instabilities that grow faster than any conceivable feedback mechanism could correct them. The timescale for this instability to destroy the bubble was calculated to be extraordinarily short. For a bubble operating at superluminal effective velocity, the instability would grow on timescales comparable to the light crossing time of the bubble wall thickness. Given that the wall thickness is measured in Planck lengths for high-speed bubbles, this means the instability would develop in Planck time units, approximately 10 to the negative 43 seconds. The bubble would not last long enough for a photon to cross a single atomic nucleus. It would collapse before it meaningfully existed. These three structural failures, radiation accumulation, the horizon control problem, and semi-classical instability, compounded the energy problem into a comprehensive case against physical realizability. The warp bubble did not have one fatal flaw. It had at least 4 independent fatal flaws, each sufficient on its own to render the concept non-functional, and all of them simultaneously present in any version of the Alcubierre geometry that operated at superluminal effective velocity. The situation was not a wall with a single locked door that might someday be opened. It was a fortress with multiple independent defense systems, each one capable of stopping any approach independently. It was against this backdrop of accumulating impossibilities that the most prominent episode of public confusion about warp drive research occurred. In 2012, Harold White, an engineer at NASA's Johnson Space Center who went by the nickname Sonny, presented work at a conference suggesting that modifications to the warp bubble geometry could reduce energy requirements significantly. White proposed reshaping the bubble from a thin, flat ring into a thicker, rounded toroidal configuration. His preliminary calculations suggested this modification might bring the exotic matter requirement down from planetary masses to something on the order of several hundred kilograms, a reduction of many orders of magnitude from previous estimates. The media response was immediate, explosive, and wildly disproportionate to what White had actually proposed. Headlines announced that NASA was working on a warp drive. Articles in major publications declared that faster-than-light travel was within reach of current physics. Social media platforms exploded with excitement and speculation. The story was shared millions of times across every conceivable platform. Illustrations commissioned by news outlets showed sleek, futuristic spacecraft surrounded by glowing warp rings cutting through star fields at impossible speeds. Artists rendered concepts that looked like engineering blueprints despite being based on nothing more than a speculative mathematical paper. The public absorbed a narrative in which the most respected and well-funded space agency on planet Earth had officially endorsed the feasibility of interstellar travel through warped space-time and was actively building the technology to make it happen. The reality bore almost no resemblance to the headlines. White's work was entirely theoretical. It involved mathematical analysis of modified bubble geometries using computational tools to explore how changes in bubble shape affected energy profiles on paper and in computer models. It was a single researcher's preliminary exploration of one corner of the mathematical landscape, not a NASA-endorsed engineering program backed by institutional resources and commitment. NASA did not allocate significant funding to warp drive development. There was no laboratory prototype being constructed. There was no experimental apparatus designed to generate warp fields or test space-time distortion. There was no team of engineers translating theoretical geometries into hardware specifications. The agency's involvement extended to allowing one of its employees to pursue theoretical research that fell within the broad scope of advanced propulsion concepts, which is something NASA routinely does with dozens of speculative ideas across multiple research centers, the vast majority of which never progress beyond initial theoretical analysis and are never heard from again. White also conducted a small laboratory experiment using a modified White-Jude warp field interferometer, a tabletop device designed to detect microscopic space-time perturbations. The experiment claimed to have measured a tiny anomalous signal that might be consistent with a microscopic warp effect. The physics community received this claim with deep skepticism. The measured signal was extraordinarily small, well within the range of systematic errors and environmental noise that plague sensitive interferometric measurements. No independent replication confirmed the result. The experimental setup faced numerous criticisms regarding potential confounding factors. Subsequent analyses suggested the signal was most likely an artifact of thermal fluctuations or electromagnetic interference rather than a space-time effect. This episode illustrates a pattern that has repeated throughout the history of warp drive research and continues to generate confusion today. A theoretical physicist or engineer publishes a paper exploring some mathematical aspect of warp geometry. The paper contains appropriate caveats about the theoretical nature of the work and the enormous gap between mathematical analysis and physical realization. Media outlets strip away the caveats, amplify the most exciting interpretation, and present the work as a step toward building an actual warp drive. The public absorbs the amplified version. Scientists then spend years correcting the misunderstanding, while the original inflated narrative continues circulating on social media and in popular science articles that never receive corrections. The damage from these media cycles extends far beyond simple misinformation about a single scientific topic. They create an accumulated, sedimentary layer of public expectation that warp drive research is progressing steadily toward engineering reality, when in fact, the entire field remains firmly and exclusively within the domain of theoretical mathematics. Each cycle deposits another layer of false confidence. Each headline makes the public slightly more convinced that practical warp drives are approaching feasibility within some imaginable timeframe. Each breathless article makes it harder for working scientists to communicate the actual state of the research honestly, without seeming like pessimistic killjoys who refuse to share in what appears to be justified excitement over genuine progress. The gap between public perception and scientific reality grows wider and more entrenched with each media cycle, and closing that gap requires precisely the kind of careful, patient, nuanced explanation that modern headlines and social media platforms are structurally designed to prevent. The format rewards excitement and punishes accuracy. The incentives point in exactly the wrong direction for communicating the subtleties of theoretical physics to a general audience. White's geometric modifications regardless of how they were reported, did not solve the fundamental problems facing the warp concept. His energy estimates were based on preliminary calculations that other researchers found difficult to reproduce. Even accepting his most optimistic figures, the requirement for negative energy density remained. The exotic matter problem persisted. The radiation accumulation, horizon control, and stability issues were not addressed by reshaping the bubble from a ring to a torus. The modifications adjusted one parameter of an impossible equation without affecting the impossibility itself. By 2020, the field had reached a peculiar kind of equilibrium. Every barrier identified over the preceding decades remained firmly in place. Not one had been removed. Not one had been weakened by any proposed modification. The exotic matter requirement persisted at the bottom of every calculation. The structural failures stood unchallenged and unresolved. 3 decades of mathematical exploration had mapped the problem with extraordinary precision without finding a single viable path through it. Meanwhile, the public, shaped by years of breathless headlines, believed real progress was being made toward an actual warp drive. The physics community knew better. The gap between those two understandings was vast and growing wider with each passing year. What made this equilibrium so unusual within theoretical physics was its durability. Most speculative ideas in physics either get disproved and disappear from the literature or find experimental support and graduate into mainstream research programs. The warp bubble did neither. It could not be disproved because the mathematics was valid. It could not be promoted because the physics was absent. It occupied a category almost unique in modern theoretical research, a result that was simultaneously correct and useless, proven and empty, rigorous and irrelevant. Journals continued accepting papers about it because the mathematical content met peer review standards. Funding agencies continued declining to support it because no experimental program could be designed around it. Conference talks about warp geometries attracted curious audiences and polite applause, but generated no follow-up collaborations aimed at laboratory work. The idea existed in a kind of intellectual purgatory, too legitimate to ignore and too impractical to pursue. This purgatory had a corrosive effect on the small community of researchers who continued working on the problem. Theoretical physicists who published papers exploring warp geometries sometimes found their work dismissed not on mathematical grounds, but on grounds of perceived frivolity. The association with science fiction, amplified by decades of media distortion, made the topic professionally risky in ways that purely mathematical questions about space-time geometry should never have been. Some researchers avoided the subject entirely despite genuine theoretical interest. Others published under framing that carefully avoided the word warp, describing their work in terms of exotic space-time geometries or modified vacuum solutions to distance themselves from the cultural baggage the concept carried. And yet, despite all of this accumulated impossibility, the equations themselves had not changed. The mathematical landscape of general relativity still contained the warp geometry. It still permitted the shape. The shape still described a configuration of space-time that could carry an object across cosmic distances without violating local speed of light limits. The theory still allowed it. Physics still appeared to forbid it, and that tension between mathematical permission and physical prohibition is exactly what kept a small handful of theorists working on the problem long after the mainstream had moved on. Because in theoretical physics, mathematical permission matters. A valid solution to Einstein's field equations is not easily dismissed. It sits in the mathematical landscape like an unexplored cave, dark and inaccessible but undeniably present. You can argue that the cave leads nowhere. You can point out that every path into it is blocked by rockfalls. You can demonstrate that the air inside is unbreathable and the walls are unstable, but you cannot pretend the cave does not exist. It is there. The equations say so, and the equations have been right about everything else. Throughout the late 2010s, a small community of researchers continued publishing papers that explored the mathematical properties of warp-like spacetime geometries. They were not trying to build a warp drive. They were not claiming breakthroughs. They were doing what theoretical physicists do. They were mapping the landscape of solutions to Einstein's equations, probing the boundaries of what the theory permits, and testing whether the assumptions that made the warp bubble seem impossible were truly as rigid as everyone believed. The energy conditions, those foundational assumptions preventing exotic geometries from being realized in the physical universe, had always been assumptions rather than proven theorems derived from first principles. They were motivated by observation and by decades of experience with ordinary matter. They were supported by every measurement ever taken, of every form of matter and radiation in every laboratory and telescope on Earth and in space. But they were not derived from first principles in the same rigorous way that conservation of energy is derived from time translation symmetry through Noether's theorem, or conservation of momentum is derived from spatial translation symmetry through the same mathematical framework. The energy conditions were empirical generalizations, patterns observed in nature, and elevated to the status of axioms because they had never been violated at macroscopic scales. And in physics, the history of science teaches us repeatedly that empirical generalizations sometimes encounter exceptions when the conditions change in ways that push beyond the regime where the generalizations were originally established. What is universally true in one domain of physics sometimes turns out to be approximately true, or conditionally true, or not true at all in a different domain. Quantum field theory had already shown that the weak energy condition could be violated locally and temporarily, through the Casimir effect and through other quantum phenomena involving vacuum fluctuations in curved spacetime. Backgrounds. The violations were tiny, fleeting, and confined to microscopic scales, but they existed, they were real, and their existence raised a question that refused to go away. Could those violations be extended, amplified, or restructured in ways that might produce geometries resembling a warp bubble without requiring the catastrophic quantities of exotic matter that had doomed the original concept? Between 2020 and 2025, a series of papers began appearing that approached this question from entirely new mathematical directions. The researchers involved were not wild-eyed dreamers publishing in fringe journals or self-appointed visionaries making grandiose claims on social media. They were trained relativists and mathematical physicists working within the established mathematical framework of general relativity, employing rigorous analytical and computational techniques to probe a problem that the wider community had largely abandoned as a dead end. They published in peer-reviewed journals. Their work passed the scrutiny of expert referees. Their mathematics was checked and rechecked. Their results did not solve the warp problem. They did not announce breakthroughs or hold press conferences. They did not claim that warp drives were coming or that humanity was on the verge of interstellar travel. What they did was something far more subtle, far more careful, and far more genuinely interesting to the future of theoretical physics than any headline could capture. They found classes of solutions that nobody had previously thought to look for, solutions that lived in corners of the mathematical space that earlier analyses had overlooked or dismissed without full exploration. And those solutions changed the terms of the conversation in ways that even the most committed skeptics in the general relativity community had to acknowledge as mathematically legitimate and theoretically significant. What those solutions actually contained, what they genuinely mean for the future of physics, and why they still do not bring humanity 1 millimeter closer to the stars, requires its own careful examination. In 2021, a physicist named Eric Lentz published a paper that did something no one in 30 years of warp research had managed to accomplish. He constructed a class of spacetime geometries that resembled warp bubbles and that did not require negative energy density. The paper appeared in the journal Classical and Quantum Gravity, the same journal where Alcubierre had published his original metric nearly 3 decades earlier. The title was technical and understated, as physics papers tend to be. The content was anything but understated. Lentz had identified a family of soliton solutions to Einstein's field equations, self-reinforcing wave-like configurations of spacetime curvature that propagated through space while maintaining their shape, carrying a region of flat interior spacetime along with them. The critical difference from every previous warp geometry was that these soliton solutions could be sourced entirely by matter and energy with positive energy density. No exotic matter, no energy condition violations, no negative energy below the quantum vacuum baseline. The mathematical ingredients were, at least in principle, the kind of energy that actually exists in the physical universe. This was a genuine surprise. 3 decades of analysis had established what appeared to be an iron law of warp geometry. If you want to contract space ahead and expand space behind a bubble, you need negative energy. Period. Every variation, every optimization, every clever geometric trick had bumped against this same wall. Lentz did not climb over the wall or tunnel through it. He walked around it by changing the question. Instead of asking how to build an Alcubierre-style bubble with less exotic matter, he asked whether entirely different space-time geometries could produce similar transport effects using only positive energy configurations. The answer, to the surprise of much of the relativity community, was yes. Under specific mathematical conditions, such geometries existed within the solution space of Einstein's equations. But before this result can be properly understood, and before it can be properly contextualized against the hype it inevitably generated, the precise meaning of what Lentz found must be laid out with care. Because what the paper actually demonstrated, and what the public believed it demonstrated, are separated by the same enormous gulf that has plagued this field since 1994. A soliton in physics is a wave packet that maintains its shape as it propagates through a medium. Unlike ordinary waves that spread out and dissipate over time, losing their coherence and eventually disappearing into background noise, solitons hold together indefinitely because nonlinear effects in the medium counterbalance the natural tendency of the wave to disperse. The wave wants to spread, the medium pushes back. The result is a stable, self-reinforcing packet that travels without degrading. Solitons appear in many areas of physics, from water waves in narrow channels, first observed by Scottish engineer John Scott Russell in 1834, to pulses of light in optical fibres that carry internet traffic across ocean floors. They are well understood mathematical objects with rich theoretical foundations spanning nearly 2 centuries of study. Lentz applied this concept to space-time itself, treating the fabric of the universe as the medium through which a soliton-like distortion could propagate. Instead of a static bubble geometry that must be sustained by a continuous external distribution of exotic matter pressing against the natural tendency of space-time to flatten out, he proposed a dynamic space-time configuration that propagates as a self-sustaining wave through the fabric of space. The geometry moves because the wave moves. The configuration holds together because the nonlinear properties of Einstein's field equations, which describe how space-time curvature feeds back on itself, provide the stabilizing mechanism that prevents dispersal. The soliton approach offered several theoretical advantages over the traditional Alcubierre framework. Because the configuration is a propagating wave rather than a static structure, the energy requirements take a different mathematical form. The energy density at every point in the soliton geometry can remain positive, satisfying the weak energy condition that the original Alcubierre metric so thoroughly violated. The total energy is still enormous, a point that requires emphasis and will receive it shortly, but its character changes from physically impossible to physically conceivable. Positive energy is something the universe contains in abundance. Stars radiate it, nuclear reactions produce it, mass itself embodies it, through Einstein's equivalence of mass and energy. The shift from requiring energy that does not exist to requiring energy that does exist, even in impractical quantities, represents a genuine conceptual advance in the mathematical understanding of what space-time geometries are permitted. Lentz was not the only researcher exploring this territory during this period. Between 2021 and 2025, a small but remarkably productive community of theorists published a series of papers that collectively expanded the known landscape of warp-like space-time solutions in directions that previous decades of research had not explored, and, in some cases, had not imagined. Alexei Bobrik and Gianni Martire published work in 2021 that established a general classification framework for warp-drive spacetimes, categorizing the relationships between bubble geometry, energy conditions, and effective velocity in a systematic and comprehensive way that had not previously existed in the literature. Their analysis clarified which combinations of geometric properties were mathematically consistent within general relativity and which combinations led to contradictions. This provided a detailed map of the solution space that subsequent researchers could navigate far more efficiently than the piecemeal explorations that had characterized earlier decades of work. Instead of individual researchers stumbling upon specific solutions through trial and error, the field now had a taxonomy, a structured understanding of how different geometric choices led to different physical requirements. Researchers also revisited the Notario-style warp geometries with fresh mathematical tools and techniques that had not been available or had not been applied to this problem during the original analyses. The original Notario formulation from 2002 had proposed a warp mechanism based on a sliding motion of spacetime, rather than the Alcubierre-style symmetric expansion and contraction. This zero expansion approach avoided some of the most severe energy problems, but not all of them. New analyses applied to the Notario framework between 2022 and 2024 showed that modified versions of the sliding geometry, incorporating insights from the Soliton approach and from the Bobrick-Martier classification, could further reduce the severity of energy condition violations. In some highly constrained configurations with very specific geometric parameters, the violations could potentially be eliminated entirely for subluminal effective velocities. The qualifier subluminal is critically important and will be addressed directly in what follows. Other researchers explored what happens when you modify the shape of the warp shell itself. The original Alcubierre metric used a specific mathematical function to define the bubble wall profile. That function was chosen for mathematical convenience rather than physical optimality. By exploring alternative wall profiles, researchers found that certain shapes distributed the energy requirements more favorably than others. Some profiles concentrated energy in ways that reduced peak energy densities while maintaining the overall geometric effect. Others distributed energy more uniformly across thicker bubble walls, trading intensity for volume in a way that brought the energy profile closer to satisfying the weak energy condition. The collective result of this research activity between 2021 and 2025 was a substantial expansion of what physicists understood about the mathematical possibilities for warp-like spacetime geometries. The landscape turned out to be far richer than anyone had appreciated during the first 3 decades of warp research. The original Alcubierre metric was not the only way to construct a bubble-like spacetime. It was not even the best way. It was simply the first way. The geometry that happened to be discovered in 1994, and its specific properties, including its extreme energy requirements, reflected its particular mathematical construction rather than any universal feature of all possible warp geometries. This is the genuine scientific content behind headlines announcing the closest thing to a warp bubble. Researchers demonstrated that the space of mathematical solutions to Einstein's equations contains warp-like geometries that are less pathological than the original Alcubierre metric. Some of these geometries can be sourced by positive energy alone. Some reduce the magnitude of energy condition violations. Some avoid specific structural problems that plagued the original formulation. These are real mathematical results published in peer-reviewed journals and verified by independent analysis. They represent genuine progress in understanding the geometric possibilities that general relativity permits. Now comes the part that separates scientific communication from science fiction marketing. Because every single one of these results comes attached to limitations so severe that the phrase "closest thing to a warp bubble," while technically accurate, communicates almost nothing about the actual state of affairs. Start with the energy magnitudes. The Lentz-Soliton solutions require positive energy, which is a genuine and meaningful conceptual improvement over the negative energy demanded by the original Alcubierre metric. But the quantity of positive energy required remains staggering, beyond any physically meaningful context, beyond any scale that connects to human experience or human capability in any foreseeable future. Estimates for a soliton configuration capable of transporting a modest payload, something the size of a small room, at even a significant fraction of the speed of light, place the energy requirement at approximately the total mass energy content of a planet the size of Jupiter or larger. Not the thermal energy Jupiter radiates into space. Not the kinetic energy of Jupiter in its orbit around the Sun. Not the gravitational binding energy holding Jupiter together. The total mass energy of every single atom in the entire planet, all of its hydrogen and helium and trace elements, converted completely and perfectly into usable energy through flawless mass energy conversion with 100% efficiency, leaving nothing behind, and then focused with absolute mathematical precision into a shell geometry thinner than an atomic nucleus surrounding the transported payload. Every atom, every particle, the entire planet consumed and converted and shaped into a geometric configuration of space-time curvature. That is the energy budget for traveling slower than light, using the most favorable warp geometry ever discovered. Humanity's total annual energy production across all sources, every power plant, every solar panel, every nuclear reactor, every barrel of oil burned across the entire surface of the Earth, amounts to approximately 580 exajoules. The mass energy content of Jupiter is approximately 1.7 times 10 to the 44th joules. The ratio between these two numbers spans roughly 23 orders of magnitude, 23 powers of 10. To generate the energy required for even the most optimistic soliton warp configuration, humanity would need to multiply its entire current annual energy output by a factor of approximately 100,000 trillion, and sustain that output continuously while channeling every joule into a single geometric structure of subatomic thickness. This is not a gap that technology closes in decades or centuries or millennia. This is a gap that separates current human civilization from the energy manipulation capabilities of a hypothetical civilization so incomprehensibly advanced that our entire species and everything it has ever built would be a microscopic footnote in its history. The positive energy requirement represents a genuine improvement over the negative energy requirement in exactly one narrow but important respect. The energy now belongs to a category that physically exists somewhere in the universe. It does not belong to a category that any foreseeable civilization operating under the known laws of physics could produce, concentrate, shape, sustain, and deploy. Next, consider the velocity limitation. This constraint is perhaps the most significant of all the limitations facing the recent positive energy solutions, and simultaneously the most frequently omitted from popular discussions of the research. The Lentz-Soliton solutions and the substantial majority of positive energy warp geometries identified between 2021 and 2025 achieve their favorable energy properties specifically and exclusively. At subluminal effective velocities, they describe space-time configurations that transport a payload at speeds below the speed of light, not above, not at, below. The bubble moves through space at a rate that does not exceed the cosmic speed limit, even though the mechanism of transport is fundamentally different from conventional propulsion. This distinction matters enormously because the entire original appeal of the Alcubierre metric, the reason it captured imaginations across physics and popular culture alike, was its promise of superluminal effective travel. The ability to cross interstellar distances faster than light could traverse the same path through undistorted space was the revolutionary core of the proposition. It was what separated the warp concept from every other proposed interstellar transportation mechanism. A subluminal warp bubble does not deliver this promise. It describes a space-time geometry that moves a payload through space at speeds that could in principle be achieved through conventional acceleration using rockets or other propulsion technologies, albeit through a completely different and theoretically fascinating physical mechanism. The geometry is novel. The physics is interesting for what it reveals about space-time, but it does not solve the fundamental problem of interstellar distance that motivated the original search. A subluminal warp configuration traveling at 90% of light speed would still require approximately 4.9 years to reach the nearest star system, Alpha Centauri. A conventional spacecraft accelerated to the same velocity through rocket propulsion would arrive at exactly the same time. The warp bubble would provide no advantage in transit time over a sufficiently powerful conventional engine, which rather dramatically undermines the original motivation for investigating warp geometries in the first place. The positive energy solutions that do claim superluminal effective velocity face additional scrutiny. When researchers examined whether the Lentz-Soliton framework could be extended to superluminal speeds while maintaining positive energy density everywhere, the results were ambiguous and contested. Some analyses suggested that pushing the Soliton velocity above light speed reintroduced energy condition violations in certain regions of the geometry. Others argued that the violations could be confined to regions small enough to be physically acceptable. The debate remains unresolved as of 2025, with different research groups reaching different conclusions depending on the specific mathematical assumptions and approximations employed. Then there is the question of idealization, the gap between the mathematical conditions under which these solutions exist and anything resembling physical reality. Every positive energy warp geometry identified in the recent papers operates under mathematical conditions that are extraordinarily, almost comically far from anything physically realizable in the actual universe. The solutions assume perfect geometric symmetry maintained to infinite precision across the entire bubble structure, with no deviation, no fluctuation, no imperfection of any kind at any point in the geometry. They assume energy distributions that must be controlled with an accuracy far exceeding any known physical process, any conceivable manufacturing tolerance, any measurement precision ever achieved in any field of science or engineering. Real matter fluctuates. Real energy distributions contain imperfections. Real physical systems deviate from mathematical ideals. These solutions tolerate no deviation whatsoever. Some solutions require the spacetime geometry to extend infinitely in certain directions, meaning the mathematical solution technically occupies all of space in at least one dimension, rather than being confined to a finite region that could meaningfully be called a vehicle or a bubble. Others require specific and highly unusual relationships between the energy density and pressure of the sourcing matter, relationships that no known substance, field, particle, or quantum state satisfies. Even though the energy density itself is positive, the matter must behave in ways that nothing in the standard model of particle physics behaves. It must have properties that have never been observed in any experiment conducted at any energy scale accessible to human technology. Positive energy density is necessary, but not sufficient for physical realizability. Matter must also have an equation of state, a relationship between its pressure and density that corresponds to some actual physical substance or field. Many of the positive energy warp solutions require matter with equations of state that do not correspond to any known material. The energy is positive, satisfying one constraint, but the detailed properties of the matter are unlike anything observed in nature, failing a different constraint. The solutions have cleared one hurdle by eliminating negative energy, only to encounter another hurdle in the form of matter properties that remain physically unrealized. These limitations do not diminish the mathematical significance of the recent results. They genuinely expand our understanding of what Einstein's equations permit. They demonstrate that the landscape of warp-like solutions is more varied and in some ways more favorable than 3 decades of research suggested. They open new avenues for theoretical exploration that may produce further surprises. The mathematical contribution is real and valuable to the field of general relativity, regardless of whether any practical application ever emerges. But mathematical permission and physical realization remain separated by the same category of gulf that has characterized this field from the beginning. The distance between the two has perhaps narrowed slightly. The impossibility has shifted from absolute to merely astronomical. Where the original Alcubierre metric required energy that does not exist in any form anywhere in the universe, the newer solutions require energy that exists in principle but exceeds human capability by factors that make the word impractical sound absurdly optimistic. The barrier has changed character without changing magnitude in any operationally meaningful way. This is what the closest thing to a warp bubble actually means, and it is important to state it plainly because the phrase itself invites misunderstanding. No warp drive is being built. No faster-than-light travel is approaching feasibility. No experiment has confirmed any aspect of warp geometry in a laboratory. No engineering is underway. No prototypes are being designed. No timelines can be estimated for when such technology might emerge. None of these things are true. None of them are close to being true. What has happened is that the mathematical terrain surrounding an old and famous equation has been explored more thoroughly than before, and the exploration revealed features that previous generations of researchers missed. Understanding why that matters, why pure mathematical discovery deserves attention even when it leads nowhere practical, requires thinking about what theoretical physics is actually for. General relativity is more than a practical tool for predicting planetary orbits and designing GPS satellites. It is humanity's deepest mathematical description of how spacetime itself behaves. Every solution to its equations, whether physically realizable or not, teaches something about the nature of space and time. Black hole solutions taught us that spacetime can curve so severely that nothing escapes. Cosmological solutions taught us that the universe is expanding and that space itself has a history. Gravitational wave solutions taught us that spacetime can ripple like a pond and carry energy across cosmic distances. Each of these mathematical discoveries advanced human understanding of reality in ways that transcended any immediate practical application. The warp bubble solutions belong in this tradition. They teach us that space-time geometry permits configurations more exotic and more varied than intuition suggests. They reveal that the relationship between energy conditions and geometric possibilities is subtler and more complex than physicists assumed for most of the 20th century. They demonstrate that general relativity contains mathematical depths that are still being explored 110 years after Einstein published the theory. Whether or not a warp bubble is ever physically produced, the mathematical exploration of these geometries enriches our understanding of the theory that governs the large-scale structure of the universe. There is something worth sitting with in this realization, something that connects the warp bubble research program to a much older and deeper human question about our place in the cosmos. Humanity inhabits a single planet orbiting a single unremarkable star in an outer arm of an ordinary spiral galaxy. The nearest neighbouring star system lies approximately 4 light-years away, a distance so vast that the fastest spacecraft ever launched by human hands, the Parker Solar Probe, at its peak velocity of approximately 400,000 miles per hour, would require more than 6,000 years to cross it. The galaxy itself spans 100,000 light-years from edge to edge. The observable universe extends 46 billion light-years in every direction from where you are sitting right now listening to these words. These distances are not merely inconvenient obstacles to be overcome by the next generation of propulsion technology. They are barriers of a kind that no technology currently imagined, no engineering program currently conceived, and no physical principle currently understood can overcome within any time frame meaningful to individual human lives or even to human civilization as a whole. The cosmos is built on a scale that dwarfs biological intelligence and may permanently exceed its reach. The warp bubble research program, for all its theoretical beauty and mathematical ingenuity, has not changed this fundamental reality. It has shown that Einstein's equations contain geometric shapes that would, if somehow produced, allow effective superluminal travel. It has shown that some of these shapes require less pathological energy than others. It has shown that the mathematical landscape of possibilities is richer than expected, but it has not produced a single physical mechanism for generating any of these geometries. It has not identified any pathway from theoretical solution to experimental realization. It has not bridged the gap between what the equations permit and what the universe provides. And that gap, measured honestly, remains as wide as ever, not because physicists lack imagination or because society fails to prioritize the right research, The gap exists because the requirements documented throughout this story belong to a category that has no precedent in the history of technology. Every previous barrier humanity has overcome, from heavier-than-air flight to nuclear energy to computing at the quantum scale, involved problems where the physics was understood and the engineering was missing. The warp problem is the inverse. The engineering is not even wrong, to borrow Wolfgang Pauli's famous phrase. It cannot begin because the physics offers no starting point. There is no material to shape, no field to harness, no reaction to trigger, no process to scale up. The equations describe a destination with no road leading to it. These are not problems that will be solved by next year's paper, or next decade's telescope, or next century's technology. They are problems that may define a boundary unlike any humanity has previously encountered. Not a wall of ignorance that research will eventually dismantle, but a wall built into the architecture of physical law itself. Previous walls in science concealed doors that opened when the right key was found. This wall may contain no door at all, or it may contain a door visible only to a physics we have not yet developed. Honesty demands admitting both possibilities without favouring either. Or they may not. That is the honest answer, and honesty is what this subject desperately needs after 3 decades of hype. Physics has surprised humanity before. Phenomena, once considered impossible, have turned out to be routine features of the natural world. The history of science counsels both humility about what we claim to know and realism about how much remains unknown. The warp bubble may indeed represent a permanent impossibility, a mathematical ghost that will never be clothed in physical substance. Or it may represent an early glimpse of possibilities that a more complete understanding of physics, perhaps a theory of quantum gravity that unifies general relativity with quantum mechanics, might someday illuminate from a completely unexpected direction. What the research between 2022 and 2025 actually achieved was not a step toward building a warp drive. It was not a prototype. It was not a proof of concept. It was not an engineering milestone of any kind. What it achieved was a step toward understanding the mathematical universe that Einstein's equations describe, a universe of geometric possibilities that exists within the theory of general relativity, independent of whether any of those geometries can be produced by physical processes in the actual cosmos. That mathematical universe is stranger, more varied, and more geometrically rich than anyone appreciated in 1994 when Alcubierre first opened this line of inquiry. The solutions that Lentz, Bobrick, Martyr, and others identified are genuine and valuable contributions to human knowledge about the nature of spacetime and the structure of Einstein's equations. They deserve recognition and respect on those precise terms, neither inflated by media hype into engineering breakthroughs that they emphatically are not, nor dismissed by cynical observers as irrelevant mathematical games that serve no purpose. They are theoretical physics. They map the territory of what is mathematically possible. And mapping that territory is one of the most important things that human minds can do, regardless of whether every feature on the map corresponds to a destination we can physically reach. The closest thing to a warp bubble is not a machine. It is not a prototype. It is not a glowing ring of exotic energy surrounding a spacecraft in a laboratory. It is a set of equations written on paper and verified by computation showing that Einstein's theory of general relativity, the most thoroughly tested description of gravity and spacetime in human history, permits geometries that are slightly less impossible than we previously believed. The impossibility has been refined. The landscape has been mapped more completely. The mathematical richness of general relativity has revealed new features that a century of exploration had not uncovered. That is the truth. It is less exciting than the headlines. It is less dramatic than the social media posts. It is less satisfying than the narrative of human ingenuity conquering the stars. But it is honest. And in a field that has been plagued by hype, misunderstanding, and the chronic inflation of theoretical results into engineering promises, honesty is the most valuable commodity available. The universe does not owe us warp drives. It does not owe us interstellar travel. It does not owe us anything beyond the physics it contains. What it has given us, Through the work of Alcubierre, Lentz, and every theorist who explored the strange geometric corners of Einstein's equations, is a deeper understanding of the space-time we inhabit. Whether that understanding ever leads to the stars, or whether it remains forever a map of territory we can describe but never visit, it represents something remarkable. A species confined to a thin shell of atmosphere on a small rocky world looked at the equations governing reality and found shapes in them that no one expected. The shapes may never become ships, but the finding itself is worth the journey.